When somebody tells you atoms are 99, 99 empty space, it sounds like a trick sentence. It sounds like the kind of fact you repeat at a party to look clever, and then everyone nods and goes back to eating chips. But if you take it seriously, it becomes a completely disturbing idea. Because you immediately think, if I'm almost entirely empty, and the chair is almost entirely empty, then why can't I pass right through the chair? Why does the chair hold me up? Why does the floor stop me? Why does a wall stop a bullet? If the universe is basically emptiness, what is doing all the work? Here's the thing, your everyday sense of solidity is not caused by atoms being tightly packed like little marbles with no gaps. It's caused by rules, very strict rules, about how electric charges in quantum states are allowed to overlap. The empty space inside atoms is not like an empty box with nothing happening. It's filled with influence. It's filled with electric fields and with a kind of bookkeeping for what electrons are allowed to do. The miracle is not that matter is empty. The miracle is that matter is stable. And this isn't some dreamy philosophical speculation. We can measure this. The experiments prove it. We can take beams of particles and fire them through thin layers of matter, and we can see what gets through and what gets deflected. We can take light and look at the spectra of atoms and see the fingerprints of their internal rules. We can take microscopes that feel the surface atom by atom. Reality is stubborn. It doesn't care what you wish were true. It behaves the way it behaves, and it's our job to understand it. So let me connect it to you. Every time you clap your hands, every time you tap a screen, every time you lean on a table, you are participating in a deep physical negotiation between clouds of electrons. Your hand never truly touches the table in the naive sense. What happens is, closer to this, you bring two intricate electrical ecosystems near each other, and the universe says, no, you don't get to put those electrons in the same place in the same way. And you feel that refusal as pressure. It's beautiful and terrible. Beautiful because a few simple principles create the entire stability of the world. Terrible because the same underlying forces in other arrangements can release energies that flatten cities and boil oceans. The same kind of atomic bookkeeping that holds your bones together also holds the trigger for nuclear reactions. Nature is unified that way. You don't get separate laws for comfort and catastrophe. Now, if we're going to do this in a way that's honest, we should start where you start, the ordinary world. Then we zoom in until the ordinary becomes strange, and then we zoom out until the strange becomes universal. And in the end, you should be able to look at your own hand with a different kind of respect, not mystical respect, but informed respect. A respect for how unbelievably precise the world has to be for you to exist at all. Let's begin with the simplest act. You press your finger against a tabletop. You do it without thinking. You expect the table to push back. If it didn't, you'd be in trouble. But what is pushback? You might think you're feeling the atoms of your finger banging into the atoms of the table like billiard balls. That image is natural because it matches our everyday experience. Objects collide. But that's not what's happening at the microscopic level. Suppose we do an experiment in your mind. Imagine you could shrink yourself down not just to the size of a dust mite, but smaller, down to the scale where the atoms themselves are like planets. Now you look at the atoms in your finger. You see nuclei, tiny, incredibly dense centers. And around them, not little beads on circular tracks, but fuzzy regions where electrons are likely to be found. That fuzziness is not because we don't have good microscopes. It's because the electron does not have a single definite position the way a marble does. It has a probability distribution, a wave-like character that spreads out. Now you drift toward the atoms of the table. Between the nuclei, there is enormous space compared to the size of the nuclei. That's where the 99% empty phrase comes from. If the nucleus were the size of a pea, the atom might be the size of a stadium. The stadium is mostly air. That's the picture people mean. But now, as you get close, something happens that the stadium picture doesn't capture. The electrons in your finger and the electrons in the table start to interact. They repel electrically because they have the same charge. And more than that, they are restricted by a deeper principle. They cannot all pile into the same quantum state. They have to arrange themselves into distinct patterns. This is the part that makes solidity feel like a law rather than a material property. The stuff of solids is not like bricks, it's like rules. Think about a crowd. If you have a small room and you try to push more and more people into it, at first they can stand closer. But as it gets packed, it becomes hard. Not because the people become rigid objects, but because there are only so many positions, only so many ways to arrange bodies without overlap. The resistance comes from constraints. In matter, the constraints are even more absolute. Electrons are not little people you can squeeze past each other. They are identical quantum entities with a strict accounting rule. When you try to push your finger into the table, you are trying to force the electron patterns of your finger's atoms into the electron patterns of the table's atoms. Nature refuses, and it refuses with an electrical force you can feel macroscopically. Now look at another everyday thing, smell. You open a bottle of perfume. A few molecules escape into the air. Somehow they travel across the room and end up in your nose. That means matter is not fixed, it's in motion. Those molecules are tumbling, bouncing, colliding with air molecules, nitrogen and oxygen, each collision changing direction. They wander like a drunk person in a hallway. But there are so many collisions that the drift looks smooth. This wandering is diffusion. If you warm the room, the smell spreads faster. Why? Because temperature is a measure of how violently the molecules are jiggling. The more energy they have, the more they move, the faster they explore space. That's not a metaphor. If you could see the atoms, you would see a furious dance, everything jiggling, vibrating, colliding. Now take a crystal, say a piece of salt. Salt looks rigid, orderly, unchanging. But zoom in and you find that even a crystal is alive with motion. The atoms are arranged in a regular pattern, yes, but they are not at rest. They vibrate around their equilibrium positions. The order is not stillness. It's organized jiggle. Here's a thought experiment. Imagine you could watch a single atom in that crystal for a long time, like a time-lapse movie. You'd see it shake around its position. If you cool the crystal, the shaking gets smaller. If you heat it, the shaking gets larger. If you heat enough, the pattern breaks and it melts. That is melting. The jiggle becomes so large that the ordered arrangement can't hold. Now consider water. Water is strange. It expands when it freezes, and that's why ice floats. That single fact, ice floating, changes the entire history of life on Earth because lakes freeze on top, insulating the water below, allowing organisms to survive. If ice sank, lakes would freeze from the bottom up and might solidify entirely in winter, and life as we know it would have a much harder time. Why does ice float? Because the arrangement of water molecules in solid ice is more open than in liquid water. The empty space between molecules increases. The shape of the molecule and the way it bonds makes a lattice with gaps. So even in ordinary materials, empty space is part of structure. Nature uses emptiness like architecture. Now, if everything is made of atoms and empty space, you might ask, why doesn't matter just collapse? Why don't electrons fall into the nucleus? Why does the atom have a size at all? This is where the why questions begin to bite. Why is there space in atoms? Why is the nucleus so small? Why are electrons spread out? Why do atoms have stable sizes? Why do solids resist compression? Why do you have a shape? Let me tell you, if you keep asking why, you eventually hit bedrock, principles that are not explained by deeper mechanical gears, but are described by fundamental laws we've tested relentlessly. Start with the nucleus. The nucleus is tiny and dense because it's held together by a powerful short-range force, the strong nuclear interaction. It binds protons and neutrons together, But the protons are positively charged and they repel each other electrically. So the nucleus is already a compromise, a strong force pulling inward, electrical repulsion pushing outward. It sits at a small size because the strong force is extremely strong, but only works over very short distances. Beyond that distance, it drops off fast and the protons would fly apart. That's why nuclei have a scale. Now, why don't the electrons just spiral into the nucleus like satellites losing energy and crashing into a planet? If electrons were classical little charged balls orbiting, they would radiate energy and fall in. That's a classical prediction. It's wrong. Atoms are stable. So the world is telling you something. Electrons are not classical orbiting balls. Why are electrons spread out? Because they obey quantum mechanics. In quantum mechanics, an electron bound to a nucleus is described by a wave function. The wave function has certain allowed patterns, standing waves. Only certain patterns fit, like notes on a guitar string. The electron's position is not a single point, it's distributed. The atom has a size because the lowest energy allowed wave pattern has a certain spread. If you try to confine it tighter, you change the pattern and raise the energy. Here's an experiment in your mind. Suppose you try to squeeze an electron into a smaller region around the nucleus. You might think, fine, just push it closer. But quantum mechanics says if you confine a particle to a small region, its momentum becomes uncertain and typically large. That means it has more kinetic energy. Confinement costs energy. So there is a balance. The electrical attraction wants to pull the electron closer. The quantum confinement energy pushes back. The result is a stable size. Now ask, why do solids push back when you squeeze them? Partly because the electrons repel electrically, but also because squeezing changes the allowed quantum states in a material. In a solid, electrons occupy bands of allowed energies. When you compress the solid, you alter the spacing and the overlap of atomic orbitals, and the electrons must rearrange. That rearrangement often requires energy. So the resistance to compression is not merely atoms hitting. It's the cost of forcing a quantum system into a less comfortable set of states. This is the cosmic accounting part of physics. Nature keeps track of energy. You cannot get something for nothing. If you want to push matter into a smaller volume, you have to pay energy to change the electromagnetic and quantum arrangement inside it. The table pushing back is nature presenting you with a bill. You can feel this bill when you compress a spring. You do work. Where does that work go? It goes into stored energy in the electromagnetic forces between atoms and into tiny changes in the electron distributions. Let the spring go and the stored energy comes back out as motion. The accounting balances. Now, here's a place where people get confused. They think empty space means no energy, but empty space can contain fields, and fields can contain energy. Electric fields store energy. Magnetic fields store energy. In modern physics, even the vacuum has structure. Quantum fluctuations. But don't jump too fast. We don't need fancy vacuum talk to understand why you feel solid. Even ordinary electromagnetism and the exclusion rules for electrons are enough to explain the everyday world. So what are you made of, if not mostly stuff-filling volume? You're made of patterns that persist. You are made of stable arrangements of atoms, and those arrangements persist because energy is conserved and because the allowed quantum states create barriers to rearrangement. Your body is a slow chemical fire maintained by metabolism, with atoms constantly being exchanged with the environment. You breathe in oxygen and exhale carbon dioxide. You drink water and later it leaves your body. The atoms in you today are not the same atoms you had years ago, yet you remain you because the pattern remains. That idea is simultaneously comforting and unsettling. Comforting because it means you're not a static pile, you're a living process. Unsettling because it means you is not tied to particular atoms. You are a river of matter, held in a stable shape by the same atomic laws that hold a crystal together. Now let's deepen the why cascade with a sharper question. If atoms are mostly empty space, why do they not pass through each other? Why is overlap forbidden? Imagine you could take two hydrogen atoms and try to place them in exactly the same place. Same nucleus position, same electron pattern. Classically, you might think it's possible. But quantum mechanics says identical fermions, like electrons, cannot occupy the same quantum state. This is the Pauli exclusion principle. It's not a force in the usual sense, it's a rule about counting states. But in practice, it behaves like a powerful repulsion, because to force overlap, you would have to promote electrons into higher energy states, and that costs energy. Again, the bill arrives. This is one of those great moments where physics becomes philosophy without trying. A simple rule about identity and states becomes the reason matter has volume, the reason white dwarfs don't collapse easily, the reason chemistry has a periodic table, the reason you can have a solid floor, and yes, white dwarfs. Zoom out to the cosmic scale for a moment. A white dwarf is a dead star, the remnant core of something like the sun. It's extremely dense, atoms crush so close that electrons are forced into high momentum states. The pressure that holds it up against gravity is largely an exclusion pressure, electrons resisting being packed into the same states. The same basic quantum bookkeeping that keeps your chair solid is also holding up a star against gravitational collapse. That's unity. That's the same law at two scales. Now zoom back into your fingertip on the table. The reason you can't push through is that you're not actually pushing nuclei into nuclei across empty space. You're bringing electron clouds into a region where the allowed quantum arrangements become expensive. The table's surface is an energy landscape. Your finger is another energy landscape. Their interaction produces a steep rise in energy if you try to overlap too much, and the gradient of that energy is a force. You feel that as pressure. This is why the phrase atoms are mostly empty space is dangerously incomplete. It's true geometrically, but dynamically, that space is governed. The space is full of laws. Now, what about that 99 number? It depends on how you define empty and what you mean by size. The nucleus is extremely small compared to the typical size scale of the atom. So yes, most of the volume contains no nuclear matter, but it contains electron probability, it contains fields, contains the possibility of interaction. It's not a void, it's an arena. Let's do another thought experiment. Suppose you could turn off electromagnetism just for a second while keeping everything else the same. What would happen? Chemistry would vanish. Bonds would vanish. Atoms would not hold electrons. Solids would not be solids. Your body would not be a body. In fact, the concept of a stable object at ordinary scales would disappear. So solidity is not material filling. Solidity is electromagnetic order. Or suppose you keep electromagnetism but turn off the exclusion principle. Now electrons could all collapse in the lowest energy state, and atoms would not have the rich structure they do. The periodic table would not be the periodic table. Matter would behave radically differently. The world would be alien. So what are you made of? You are made of a marriage, electromagnetism plus quantum mechanics, charges plus probability amplitudes, fields plus constraints. That marriage creates the furniture of the universe. Now, let's talk about probability, because this is where it starts to feel strange and then suddenly becomes natural. In quantum mechanics, you don't predict exactly where an electron is. You predict a probability distribution. But it's not the same as ordinary ignorance, like not knowing which card is on top of a deck. The probability is built into the best description we have of nature. Feynman's way of making this feel real is to emphasize interference. Probabilities in quantum mechanics come from adding amplitudes, numbers that can cancel and reinforce, then squaring to get an actual probability. That's the key weirdness. Nature doesn't merely pick a random path. It considers multiple possibilities, and they interfere. Imagine you could do the double slit experiment, but with electrons going through a tiny version of your table. If you send electrons one at a time through a pair of slits, you get an interference pattern, a pattern of where electrons land that looks like waves interfering. But the electrons arrive as discrete hits. So each electron behaves like a wave of possibility until it is detected. Now, what does that have to do with your solidity? A lot. Because the electrons in atoms are standing wave patterns. The allowed orbitals are interference patterns in space. The shapes of orbitals, the lobes, nodes, and symmetries, are exactly the places where the amplitude reinforces or cancels. Chemistry is interference made practical. Bonding is interference between electron wave functions of different atoms. The difference between a stable molecule and an unstable one is often a difference between constructive and destructive interference in electron probability clouds. So when you press your finger on the table, you're not colliding marbles, you're perturbing interference patterns. You're trying to force wave functions to occupy the same region. And the combined system responds by shifting into a higher energy configuration. That higher energy manifests as a force resisting compression. You are feeling quantum interference with your skin. This is where you might say, come on, that's too abstract. I'm not feeling interference, I'm feeling a table. But that's exactly the point. The macroscopic sensation is the average gigantic consequence of microscopic rules. A single electron's quantum behavior seems delicate, but a table has on the order of 1023 atoms. That's an enormous crowd. Their collective behavior is robust. The small weirdness becomes a solid certainty. And again, this isn't speculation. We can measure these effects. We can calculate the stiffness of materials from their electronic structure. We can predict conductivity, hardness, melting points using quantum mechanics. And experiments confirm it. The world is not forgiving. It either matches or it doesn't. Now let's connect this to conservation and fundamental laws. Because there's a temptation to treat empty space as a cute trivia fact, rather than part of a deeper accounting system. When you compress something, you do work. Work is energy transfer. That energy doesn't vanish, it goes somewhere. In a compressed solid, it becomes stored potential energy in electromagnetic interactions and increased kinetic and quantum energy of the electrons and nuclei in their constrained positions. When you let go, that stored energy can return as motion, sound, heat. Heat itself is a kind of hidden motion, jiggling atoms. When you rub your hands together, you are turning organized motion, your hands sliding, into disorganized atomic motion, heat. That's why your hands get warm. The friction is not some mystical property. It is the conversion of macroscopic order into microscopic disorder. Here's the terrible beauty paradox again. The same conversion that warms your hands is the general arrow by which the universe moves toward more disordered states. And yet, locally, life builds order by exporting disorder. You build a structured body by burning food and dumping waste heat into the environment. You are an order-making machine powered by disorder-making processes. Beautiful and terrible. Now zoom out again. If matter is mostly empty space, you might wonder about the universe at large. Space between atoms is large compared to nuclei, but space between stars is far larger compared to atoms. The universe is emptier than any atom, yet it's not nothing. It contains fields, radiation, particles, and it expands. The same electromagnetic laws govern both the space inside an atom and the space between galaxies. The difference is density and energy scale. And then there's relativity, which sneaks in quietly. Energy has weight. Not weight like something you feel on a scale only, but gravity responds to energy and momentum. The energy stored in fields contributes to gravitational effects. The universe keeps a full ledger. Now, you might ask, if electrons are waves of probability, why does matter look localized? Why do atoms have a clear boundary? Why does a table have a surface? Because while the wave function extends, the probability falls off. And in a solid, the electrons are in states that are largely confined to bonds and bands. The collective arrangement forms an energy barrier at the surface. The surface is a place where the allowed states change abruptly. That change produces strong forces. So the surface is a real physical region where electron distributions and potentials shift. It's not an illusion. Also, because decoherence and interaction with the environment make macroscopic objects behave classically. The quantum phases that allow delicate interference patterns get scrambled when huge numbers of particles interact with surroundings. So the table doesn't behave like a giant electron in a double-slit experiment. It behaves like a stable classical object, even though its stability is built from quantum rules. Now, come back to the opening claim, atoms are mostly empty space. So what are you made of? You are made of emptiness structured by law. You are made of nuclei that contain almost all the mass, surrounded by electrons whose distributed probability determines almost all the size. You are made of electric attraction that binds atoms into molecules and of electron exclusion that prevents collapse. You are made of a continual storm of thermal motion, even when you feel still. You are made of patterns maintained by energy flow, food in, heat out, matter exchanged. And you are made in the deepest sense of the same rules that govern everything else. The solidity of your bones and the stability of a white dwarf are cousins. The chemistry in your cells and the spectra of distant stars use the same electron rules. The warmth of your skin and the glow of a furnace are both atoms jiggling. So the next time you do something ordinary, when you pick up a cup, when you lean on a railing, when you knock on a wooden door, pause for a second and realize what you're doing. You're not just touching wood. You're testing the universe's microscopic laws with your body. You're feeling the refusal of electron clouds to occupy forbidden states. You're feeling electromagnetism's push. You're feeling quantum mechanics made into furniture. And if that doesn't change your perception a little bit, then you're not paying attention. Because in the end, the revelation is not you are empty, like a depressing punchline. The revelation is emptiness is not nothing. Emptiness is the stage where the rules act. And those rules, repeated across unimaginable numbers of atoms, become you, your shape, your strength, your fragility, your ability to hold hands with another person and feel contact. That contact is a story written in the language of atoms. Now, if you want to go even deeper, you can. You can ask why quantum mechanics is the way it is. You can ask why the electron has the charge it has, why the constants have their values, why the universe permits stable atoms at all. And at that point, you reach the edge where physics becomes a set of precise descriptions without deeper, because that we currently know. But that's not a failure. That's an invitation. Physics, at its best, is not a pile of answers. It's a way of seeing. It's a habit of refusing easy pictures when they don't match what happens. It's the courage to say, I don't understand yet, and then to keep going anyway. So you started with a strange claim, 99% empty space, and maybe you expected it to make the world less real. It does the opposite. It makes the world more real, because you realize the solid world is not an obvious thing. It's a triumph of simple laws acting consistently. And right now, as you listen, you are a collection of atoms in motion, held together by forces organized by quantum rules, exchanging energy with the air, radiating heat into the room. You are not a static object. You are a process. You are a pattern. And the universe, in its quiet, relentless way, is letting that pattern exist for now. It's beautiful and terrible, and it should make you curious.